So, welcome back. It is now my pleasure to introduce our first keynote speaker, Professor Lucia Specia from the Imperial College of London. And she has also an employment at the University of Sheffield in language engineering. Lucia has been around in the NLP field since at least 20 years. She has numerous publications. I counted yesterday something like 369 according to Google Scholar, more than 10,000 references, which is an impressive number. And I think she's been in almost all large conferences in NLP already somehow involved as shared task organizer or contributor, reviewer, and also as chair. So it is really a pleasure to have you here, Lucia. Usually when we have the on-premise conference, we know and meet the speakers beforehand. We haven't met before now, but I hope it will work well now with your keynote. You're going to talk about multimodal simultaneous machine translation, and Lucia started the first shared task already in 2016 on multimodal machine translation. So I'm curious to hear what has happened in the past 5 years in this field. Lucia, you can try to share your slides and go ahead.
Okay, good morning, everyone. Thanks for the very nice introduction and for the invitation. Very pleased to get to know one more conference, so that's very nice. Let me just get to my screen. Okay, good morning, everyone. Thanks for the very nice introduction and for the invitation. Very pleased to get to know one more conference, so that's very nice. Let me just get to my screen.
So while you connect your screen, I have a question to our audience. From teaching online, I know that it is very boring if you only look at a static screen and your own slides because you know your slides already. And it is much more entertaining for the speaker if there is some videos, some reactions on the screen. So if you have the opportunity to turn on your video, that would be really great, because then Lucia can see how people react and maybe can also react. That's great. Thank you very much.
Thank you. And apologies for the dark background. It's surprisingly sunny in London today, so I get too much light in the background. I hope you can see my screen and hear me okay.
Yeah.
So let me get started. Right, so today I'm going to talk about some of the work that we've been doing recently. My main area of research is machine translation, and this is part of it and is one type of machine translation, multimodal translation, but it's also simultaneous translation, and some people will know it as interpreting, which is another name that we give to it. And a lot of this is joint work with my postdocs, Ozan, Pranav, Julia, and Ishu, and also some collaborators from other institutions. And the work I'm presenting here is mostly summarized in 2 papers, one from last year and one from this year, and just in case you need more information about them. So I'm going to start with introducing this very briefly, this area of multimodal translation, which is a variation of machine translation, and then move on to simultaneous translation and the combination of the 2. And mainly I'm going to focus on deterministic policies, which is one type of simultaneous translation. But if we have time, I'm going to talk about dynamic policies, which use reinforcement learning. Right, so let me get started with multimodal translation. So the task of multimodal translation is, like I said, is an extension of standard machine translation. In standard machine translation, you're given a sentence or text to translate, and there is a model that generates it in another language. In this particular example, there is a word which is in English is ambiguous, hat, when translating into German. And you will know better than me, but hat could be translated differently if it's a winter hat or a summer hat or cap. And in this particular case, the system will make a decision which is almost arbitrary because we have no information to tell us which kind of hat we're talking about. So the idea of multimodal translation, and this particular type of multimodal translation that I do, is to bring visual information into the equation, images or also videos that would then help or hopefully help guide the model to choose the right translation for ambiguous words, but also for words that the model might not know, or words that are not gender marked in the source, but should be gender marked in the target, for example. And in this case, it happens to help the model to pick the correct translation of the word hat. So we organized, with great data sets, we organized a few challenges around this problem. And this is a screenshot of the results of the last challenge we did at WMT 18, which is a machine translation conference, where we compared a number of systems on the same data. And we ranked them by this geometrics, BLUE, which you might be familiar with, and Meteor, which is another string similarity metric, how close the MT output is to a human translation. And what I wanted to highlight here with these red arrows are two systems that are essentially the same, except for the fact that one of them uses visual information and the other doesn't. And the interesting and also disappointing conclusion here is that the version that uses multimodal information, this imagination version, actually performs worse than the version that doesn't use multimodal information, the text-only version. And this was for English-German. When we looked at English-French, it was the same picture. Textual system performed better. However, when we looked at English-Czech, which can be considered a slightly, well, a more complicated language pair where the two languages are more distant from each other in terms of word order and morphology, we see a very different picture. So the same system variance, now the multimodal system performs significantly better than the text-only one. So this led us to think that, well, there is actually a reason, well, there is actually a justification for this idea of using visual information to complement text information, but it's not for all language pairs and all data sets. And it's mainly for data sets where the language is challenging enough. And this again is based on a particular data set that we've been using, which is fairly simple. The vocabulary is very repetitive. The grammar is super simple. The sentences were short, on average 12 words in the source language. And there was not a lot of cases of ambiguities or noise in the input. So for most cases, language was found to be enough, but not always, as we saw for Czech. So what we decided to do after that was a very systematic study to see when and how vision can actually help text in machine translation. So this is another paper which I'm just going to give you like a couple of slides on, but essentially we are probing the need for visual information by systematically corrupting the text, the source text in this case, in various ways. And the idea is we're asking the question, if the text is either too short or it is noisy or there is not enough context, can the vision then help? And I'm just going to go over one of these probing experiments that we did, and it's easier to explain it through an example. So we took a standard, at training time, we took a standard sentence pair in the parallel corpus. For example, a dog drinks a water outside on the grass. And this was the reference which we kept intact. But on the source side, we generated various versions of it where for each iteration, we're actually masking a certain number or proportion of words. Starting from just one word, we're hiding this word. By masking, I mean we're hiding it from the model, and we're replacing the word with a placeholder, V in this case. And in another iteration, we replace 2 of the words and 3 of the words, and so on, up to a point where we only have one source word as a trigger, and everything else is just placeholders. So we still know sort of the expected length approximately of the source word, or of the target sentence as well in this case, but we don't know the words that should be there. And then we feed in the image to these models and see if those image-informed models do better than the text-only models in these cases where we have some noise that has been introduced to an extreme that we don't have a lot of information about the source sentence. And just one slide summarizing the results. The only important information here is the y-axis that shows the delta or the difference between the meteor scores of the text-only model and the multimodal model. So the higher this delta, the bigger the impact of the visual information, the positive impact of the visual information in the quality. And as you can see, as you would expect, this varies according to how much textual context we have, which is in the x-axis here. So in the extreme case where we have only one word as context, then we get up to 7 meteor points of improvement by using the visual information. And the different curves here corresponds to different multimodal systems. And what we're showing is that it doesn't really matter which architecture you're using. All of the multimodal systems will benefit from visual information when the text input is incomplete. So this was quite motivating. And just to show you an example of what that actually does to the translation, this is a real example from our data. In this case, the source said trees are in front of, and then everything else was masked. And the reference was such that trees are in front of a big mountain. The type of text here is a bit funny because it's crowdsourced data. And the text-only translation was not very good. It even didn't get right the word trees, even though it was there, and it replaced it by bicycles are in front of an outdoor building. Whereas the multimodal system here in boldface translates it correctly, trees are in front of the mountain. And you can just about see some trees there. So it actually works. So this motivated us to actually look at other applications of, or other types of translation where this type of input, incomplete input or noisy input or ambiguous input happens naturally, where we know visual information can actually help now. So, and we focus on one type of application where the input can be short or incomplete, which is the main topic of this talk, which is multimodal simultaneous machine translation. So I'm just going to introduce simultaneous MT, or what I mean by it very briefly. The first thing to mention here is that we're talking about text-to-text simultaneous translation. So there is a lot of work where you're actually going from speech to text, which is the standard setup for interpreting. But also there is work where we actually assume that there is some process of speech recognition first, of partial input, and then a translation step, which is what we do here. And the objective in simultaneous translation is to translate text as it comes. So before the sentence is complete, such that the listener doesn't have to wait to start getting the bits of text. So it's real-time translation. And that means that the translation models have to constantly make this decision about whether or not they're ready to translate, or whether they have enough context to translate, say, the first 2 words that were said, or whether they have to wait for a next word to start translating to have enough context. And what we want is to sort of maximize this joint objective that means high quality translation, but also low latency, so low waiting time for the listener. And that means we need to teach the models to do anticipation, to anticipate what is coming after the 2 words that it's read already. And when we add multimodality into the equation, the expectation is that multimodality will help with this anticipation skill that the model has to have. And just to give you an example of what we mean, so say, for example, we're translating from English into French, and we're translating a white cat. And as we know, in French, the order of adjective and noun is the reverse from English. So instead of a white cat, we would say a cat white in using French words. And if you're doing this simultaneously, if you only read, say, the first word A, you're probably not confident enough that it would be feminine or masculine, but say you get it right and translate it as a masculine, and then you get the word white, and in French, you wouldn't use that word. It's not the right word order. You'd have to wait to see what is coming next. But also it might be that if you see the word white and you have a picture and some information about this picture that tells you that there is a cat there, you can already make the decision and produce the word cat in French and continue the translation after that. So that's the expectation. And just one more clarification here is that the type of approach that we work with, we assume no retranslation. As if you've seen real-time interpreting using automatic machine translation, you might have seen that sometimes the system produces a text and then goes back and revises it, which there is a lot of, well, there's two theories or lines of thought there saying that this retranslation is actually quite tiring for the human reader, because they read something and then all of a sudden that changed, so they have to read it again from scratch. So we avoid that by saying you have to commit to one translation and then that translation is fixed. And the way we can do simultaneous translation varies. I'm going to focus mainly on what I call the deterministic policy, and this is some work that already existed for text-only simultaneous translation. And we're going to follow one of these approaches, which is called weight K, and I will explain it in a little bit. And the other type of approach, which I have some slides for, and if we have the time, we'll go over, is to actually use reinforcement learning to learn when to produce a read and when to produce a write based on some reward function that is a combination of latency and quality. And in the deterministic case, we actually predefine how many words I'm going to read before I start writing at a time, which is this K hyperparameter. So we start with the deterministic approaches, which is this paper we published last year. Before that, just a little bit on the data set that we use for all experiments. This is the standard data set for multimodal machine translation, where we have image descriptions in English. This was already some data that was already there. And we translated this image descriptions into German, French, and Czech using human translators. It's very small, about 30,000 instances. And because the sentences are very simple, such as the ones I'm showing here, this is enough to do translation here. And we call this data set multi-30K. And on the decoding and evaluation front, when we build our multimodal translation systems, we do greedy decoding instead of beam search, and that just makes the measurement of these lagging metric a lot easier. We could have some heuristics to do beam search, but we haven't done that here. We measure translation quality in blue, or in some cases Meteor as well. And then the latency we measure using this metric called average lag, which essentially gives us the number of tokens that the writer lags behind the reader. So in a way, you want this to be as low as possible. If we were able to produce one word for each word that is read, we were able to translate it, then the average lag would just be 1 here. So you're reading one word, translating one word. But in practice, to get to good quality, this average lag has to be a bit higher, because otherwise we're doing word for word translation, and we know that this is not a good strategy. But you want this number to be the lowest possible. In terms of the architectures, we implemented both sort of RNN-based architectures, which do quite well for this small data set, but also transformer-based architecture. So we have results for that, but they're very similar on this data. And we train it as standard in machine translation using maximum likelihood estimate. The only difference is that we don't look at the entire history of the source sentence at every time step. So this just means that for every word YT that the decoder produces, this is going to be conditioned on the number of source words that have been seen so far. Remember, the source is incomplete, and the number of target words that have been produced so far. So in standard neural machine translation, this is the entire source sentence, and here is just a sort of prefix that has been read so far. And this is the sort of multimodal, this is the simultaneous deterministic approach that we use, this weight K, and it's very, very simple. So you have to define what K is, and this is a hyperparameter. We do experiments with various Ks, but what it means is that you start with a prefix that is the size of K. So let's say I make sure for every source sentence, my model reads 3 source words first, so K equals 3. And then after that, for every source word that is read, I produce a translation. So I start with some context, the longer, the better, obviously, but then the longer the lag. And then after that is a one-to-one, is a word-for-word translation. And this is what I'm showing down here. If the prefix in this case was 2, I'm first reading the 2 first source words and then generating the first target word. And then after that, I read 1 word, generate 1 target word, read 1 word, generate 1 target word, and so on. And we can do this in 2 different ways. We can do this at training time and obviously test time, or we can actually train a model that we call it a consecutive model, which is just a standard neural machine translation model. And then only at decoding time, we use this weight K heuristic. And we found slightly different results in the 2 strategies, but what I think is a more principled way of doing it is actually you already train your model to do this anticipation, and then you also test it with the prefixes. So so far this was just standard simultaneous translation using this weight K strategy, deterministic policy strategy. And what I'm showing now is how we extended this to add the multimodality. And we essentially based this on our and others' previous works on multimodal translation, where we decided to implement 2 main multimodality integration approaches and 2 types of visual information. And I'm actually going to explain it with the graphs, with the figures, because it's a little easier. So one of the multimodal architectures that we use is a pretty standard one, which is the decoder attention. That means we have 2 encoders. We have one textual encoder that encodes the source sentence. We have another visual encoder that encodes the image in different ways that I will talk about. But let's just assume that there is some objects in this image that are encoded as different, as if they were almost different words. And then I have, at decoding time, I have 2 attention mechanisms, which are essentially, we're trying to learn where to look in the text and where to look in the image when generating every target word. And I combine these 2 attention mechanisms by just concatenating them. And this is one multimodal approach. The second one is what we call encoder fusion, where again, you have your 2 encoders, but you're doing self-attention between the text encoded words and the vision encoded regions, and then you only have 1 summary attention that you give to the decoder. So here the attention happens at encoding time, whereas in the previous one it happens at decoder time. In terms of visual information, again, we have 2 types of visual information. One is, well, we use this, an aside there, we use this pre-trained image networks that we use them as feature extractors, essentially, just to encode the images. We don't retrain them, we don't fine-tune them. And they have been trained to do either object classification or object detection, which is the one I'm going to talk about next. But object classification means the network is trained to classify whether the image has a subset of types of objects, whether it has a person, whether it has food, whether it has a number of things. And from that type of network, what we take is the so-called feature maps, which are in this case 64 different feature maps. And you can think about them as sort of crops of the original image, which are believed to contain potentially some object-related information, but there's no guarantee of that. And the other type of visual information is actually object detection, where the networks are trained not only to classify which objects are in the image, but also to detect where they are in the image. And this is a little bit more sort of abstract information, but also gives us a bit more guarantees that the regions that we're cropping actually have an object. And we look at 36 of these regions, which is a standard number when we're doing detection. Well, we just sort, there's more objects, but we just sort them by the confidence of the model and use the 36 that have the highest confidence. I'm going to move on to the results of using this multimodal simultaneous approach. And the first thing to cover is not yet the multimodal variant, but the consecutive baselines. This is essentially just comparing text-only machine translation and multimodal translation on this data using these architectures, but without doing the simultaneous part of it, just as a way of seeing whether the visual information helps to start with. And we're using these two types of visual information and two types of multimodal architecture. So encoder fusion and decoder attention. OD stands for object detection. OC stands for object classification. And what we observed is that, excuse me, object detection features do better overall, and decoder attention seems to do better. And what this table is showing is for two language pairs, English, German, and English, French, on three different test sets, 2016, 17, and COCO. Again, the delta, in this case, in blue scores from using the text-only model versus the multimodal consecutive model. And as you can see, apart from some red exceptions here, the multimodal model adds almost, well, in some cases, 1.7 blue points to the text-only one. So this is a good starting point. And this is different from the initial tables that I had shown, because this is a slightly sort of weaker model that's based on greedy decoding, and therefore the visual information plays a bigger role. But this is sort of a sanity check to see that things are correct. But also interesting, what we notice is that the largest improvements come from data sets or test sets that are further away from the training set. So this COCO and 2017 test sets are extracted using from a different larger set, so that they have a different distribution from the training set. So they're like, they have more out of vocabulary words, so words that haven't been seen at training time, and that's where we get a largest improvement in blue scores from using the multimodality. So here the explanation is that the multimodality is actually helping the model generate some reasonable word for those words that are not known, some reasonable translation. So overall, positive news. So let's move on to the actual multimodal variant of this. And the first thing to highlight here is, again, these are the two language pairs. These are the three types of multimodality, decoder, object detection as at the top here, the best one that we had before. And each of the colors here corresponds to a different test set. And the y-axis are again delta in blue scores. So the higher the bar, the better the multimodal model compared to the text-only one, but in this case, in the simultaneous setup. And as you can see, under low latency, meaning on the x-axis here, I indicate the k. So k equal 1 is the lowest possible latency, meaning I'm doing essentially just read one word and then start translating, read the next word, translate, read the next word, translate. We see a lot of improvement from using multimodal information, up to almost 3 blue points for one of the data sets, and for French, and then also similarly for German. But as we go or move into higher case, meaning we see more initial context before we start translating word for word, then the picture is different, and we see either very small improvement, or in some cases no improvement, which happens here to German. Actually, we see a degradation. And this is in line with what I talked about earlier in the presentation, which is the fact that when you do have long textual context, the visual information is not really needed or helpful. But we're really happy with the fact that under low latencies, meaning that you can start translating very quickly, the multimodality helps. And again, as with the consecutive models, the decoder approach using object detection performs the best. So this is the top bar here. And the encoder attention is also promising, but it's the good thing about it is that it's very efficient, because you only have essentially one attention mechanism, so it's much faster. And there's some differences across languages, which is something we always observed. And this is sort of a summary, putting a lot of things together, and there's a lot of information here, but just to summarize, everything that is blue is multimodal, everything that is gray is text only. And what we're actually comparing here is these two ways of training the models. You can train it in consecutive ways, which is what we mean by decoding only. So we only do the weight k at decoding time, or you can actually train the model using the weight k approach already, and then decode it also with the weight k. So the overall picture is showing that, well, first of all, visual information always helps, and then second, that decoder only seems to be a bit better than actually training the models, but the difference is marginal. And like I said before, it's a more principled way, while training the model with the weight k and testing it on the same setup is a more principled way of doing it. And let me just give you a couple of examples of where this helps. This is translating from English into German, and we have a weight 1 model, which is a very low latency. So, we're comparing here the text-only model and the best multimodal model. And as you can see, the text-only model, when we only see one word, a, just the article, it has to make a guess. Is it going to be the feminine or the masculine? And it picks the masculine version of the article here. It has no other information. It probably is going with the biases of the data set that has a lot more masculine articles in the target side. And with the multimodal approach, we actually already get the correct article, probably because the object detection is saying there is a woman in this picture. And as we keep translating, obviously the text-only model cannot correct that mistake, so it keeps translating everything as masculine, and the word young here gets the masculine version of that, whereas the multimodal model gets it right, and so on, until it gets to the word woman, and then we actually know that this is an incorrect translation, but then it's already too late. Another example is from English to French in this case, and it's the case of adjectives coming before nouns, and we have to swap that. So in English, it would have been a black and white bird. So again, translate the article, we actually get it right in this case, both the text only and the multimodal model. But then we have to translate the word black, and the model knows that I cannot have a color after an article. So it has to guess or to anticipate what would be the noun that would come before the word black. And in the text-only model, it anticipates a dog, which is very common in this image description data set. So it just produces dog. whereas our multimodal model actually guesses from the picture that it's a bird and translates it correctly. And then after that, it actually does a good job, but that word is already incorrect in the text-only model. Another experiment we did here, based on this, especially on this results with the article here at the top, we looked at whether multimodality was helping to get rid of some linguistic biases that we have in the data set. And in particular, we look at biases of translating the article a from English into French. And we know that in this data set, in most cases, a is translated into a masculine version of this article in French. And we wanted to check whether the multimodality is actually helping to get some of those correctly. So what we're measuring here is a proportion of time that we generate the correct article in, which is the feminine variant of a in French, when in English all it has seen is a, but the word that is coming next is woman. But it hasn't seen it yet because it's a weight one model. So, sorry, this is a better way of putting it. And what we're doing is, first we look at the text-only model here, and we actually surprisingly see that it doesn't get it right a single time. So every time we see the article a in English, before seeing anything else, the text-only model translates it as the masculine version of it in French. And this is, again, because in pretty much 70% of the training set, this is the case. There are more masculine articles than feminine articles. So when we look at the multimodal models, we see a very different picture. And for our best model, our best two models here, if we actually train the models with weight one, it gets the correct translation in 72 or 71% of the cases. So with the visual information. So that's very good news. It's just showing that obviously this is an extreme case where you only have one word, but this can happen anywhere in the sentence. And this is showing that the model is able to leverage visual information to get rid of this very strong bias that the text-only model had towards the masculine article. I already mentioned. So a couple of conclusions so far. So this was the first investigation on multimodality for simultaneous translation. And we showed that under low latency weight K approaches, the quality can improve significantly. So I haven't showed you the latency numbers here because the latency is fixed, right? If it's weight one, then the latency will be one. If it's weight two, latency will be two, and so on. So under this low latencies, we get very big improvements. And we showed that this is only because of visual information. But under higher latencies, this is not the case. We don't see any improvement. In terms of the architectures and types of visual information, using explicit object information helps the most. And using this at decoding time helps even more. And we also showed that you can help with very well-known problems in translation, such as resolving gender and also word order. There's lots of other things that we can do. Like I said, we already worked on reinforcement learning based dynamic policies. I can give you a very nutshell of the results, and they're a bit disappointing because they're very similar to the weight K. So if you want to fix under the same latency, we get the same quality, but they're still more flexible in the sense that you don't have to determine which K you're going to have. This is going to be learned by the model. So I can show you some results in discussion if you're interested. We also already worked with transformer models, but as I mentioned before, the improvements are sort of constant, both for the text-only model and for the multimodal approach. So the trends are exactly the same. We are working a lot more on this encoder side fusion because it's a much more efficient way of using or training these models so that we can train them much faster. And more interestingly, we're looking at doing the same type of work, mainly using transformer approaches and reinforcement learning, but for video translation, where the visual information is not static, but it will change as you go, as you read different source words. You'll have different frames of the video to do that. And we're looking at one particular data set that we're building called the apartment data set, where someone is describing an apartment that they want to rent out. So they're going to tell you as you they start the video, they're going to start showing you the apartment. They're going to tell you, "Oh, come in with me. This is my living room. This is the couch. This you can sit. I don't know, 5 people, and so on and so forth." They walk around and then they'll show and describe the apartment. And I'm really interested in people who want to collaborate in building this data set with translations into multiple languages. At the moment, we're doing Chinese, mainly because of the availability of speakers and researchers to collect that, but really interested in having other languages there. So let me know if you want to do that. And I think I'm going to stop here so we have time for questions. And do ask me about the dynamic policy if you want to know.
Yeah, thank you very much. I think it was very interesting, at least for me, to see a very different approach to machine translation. There have been 3 questions in the chat. I suggest that we start with these, and then the audience has the chance to just raise the hand in these reactions at the bottom of Zoom, and then I will call you, and then you can ask questions directly. So, but I suggest we start with the questions from the chat. There has been a first one by Konstantin, and I will just read it aloud, and then you can try to answer. Has there been any competitive human evaluations of multimodal machine translation quality versus neural machine translation?
Yes. So with the caveat that you need specific data, right? So I guess the question was challenges comparing text only and multimodal translation. Is that correct? Let me just reread the question.
Or maybe Konstantin, you can just comment yourself.
I'm on the street. Sorry for the noise. I wanted to say that I don't trust Blue. I want to see if there is like a human evaluation, maybe with scoring.
Yeah, yes, absolutely. So as part of the challenges that I mentioned in the beginning of the presentation, we also had human evaluation where we essentially asked humans using this standard WMT framework, which is direct assessment. We asked humans to judge the quality of both independently, both text only and MMT on a scale of 0 to 100, and we did that. And the picture was a little bit more optimistic for multimodal translation, showing that overall it's better by a margin than text only. So yes, we did do that.
Mm-hmm. Okay. So second question by Joel Niklaus. To what extent are images relevant for translation in real life scenarios where the text does not just describe the images?
Yes, very good point. So obviously this was in this image description data set, it's a very nice setup where you know there is a correspondence between the two, and it's very well defined. But you could argue that this is to some extent happens in some cases. For example, in movies where you have the audio description. So for hard of hearing people or people with hearing disabilities, so there is a textual description of what's actually. Sorry, for blind people. That's it. So where you have a description of the video for people who are not able to see it, and this is then written down and read out loud. So this is also a realistic setup where you have descriptions of some scene. But I understand the question, and in a more sort of general setup where you do have visual information and text, and whether this is whether visual information is helpful. We did look into that for general, mainly in the context of videos here, for general subtitling, but where we still expect that there will be some correspondence between the two modalities, because if there isn't any, then you might not need to ask that question at all. But the setup that we looked at was instructional videos where people were given instructions on how to do something, from like how to cook a burger to how to play the guitar. So, and there it's not really a very clear equivalence between the two modalities, because a lot of the time it's actually showing the person's face talking about how to do things, giving the instructions. But still, at certain times they will show what they're talking about. So there, it's a much harder problem. First, because it's videos, also because there is a very wide range of domains that people were talking about, and we did not see the same level of improvement from the visual information. So I think there are limitations on the type of data that you should be looking at building multimodal models. But certainly, if you expect there to be some equivalence between the two modalities, and I would say audio description for blind people, and also things like this apartment data set that I mentioned are ones where I expect there will be, and therefore the visual modality should help. But we're still working on that.
Okay, so next question. I mean, if you will have follow-up questions, just raise your hand and ask, but otherwise I would continue with the next question by Konstantin again. Would you say that NMT will be better at reducing bias of machine translation, such as gender bias coming from the historical accumulated corpora?
Yes, definitely. So there was an example which I should have shown, which was quite nice. And this was just not simultaneous translation, just multimodal translation, where you had this baseball game, and it was two women playing baseball, and all of the systems, the text was, I don't know, the baseball player ran around, or whatever the text was. But essentially, the word player, as you know, translating from English into German or French, you have to add the gender information there. And all of the systems that we benchmarked, text-only systems, translated it as a male version, because there are not many female baseball players, I guess. But the multimodal models got it right. So definitely for gender, it's a good way of trying to mitigate those biases. There was some other very funny cases on not only gender biases, other biases. For example, the word cook in our data, it always translated it. It tended to hallucinate and to add the word Asian, to say an Asian cook, without the multimodal information. Whereas when we added the picture, cooks could be all sorts of ethnicity. So we got rid of that bias as well. All right.
Okay, next question from the chat by Andrei Popescu-Belis. For the experiment with translation of English in into French 1, what are the assumptions about the most salient object in the image? Can it happen that there are two salient objects of different genders in French? And how does the MMT system behave in that case?
That is a good question. We haven't really looked at the distribution of objects for that experiment, but also, even if there were more than the two objects that corresponded to people, say there was one object that was a woman and another object that was a man or a child, or we're using this attentional MMT. So the expectation is that the model would somehow learn what is the right object as well, but there are no guarantees. So you're right. So if there is, maybe we should look into that. If there is a range of people like objects in the image and they have different genders, this could have an impact. And this might have been what happened and why we didn't get 100%, but only 72% correct in that case.
Okay, thank you. So these were the questions from the chat. So now it's open for other questions. Just raise your hand and then start your question, I suggest. And maybe I can start with one rather technical question. You mentioned that adding the images helps to reduce the errors due to out of vocabulary words. But then you would need to know in the target language the vocabulary at least.
Yes, so that is, again, I had a nice example, which I didn't put here. That is, so the out of vocabulary words can be there for various reasons. Like one of the reasons is typos. Again, this is crowdsourced data set.
Yeah.
So in typos, the assumption is that you probably do have the correct target word, but the source word, the source language has a typo. But that is one case. And the other case is, like you said, you might not actually have the target word. It's a complete out of vocabulary. And what we have seen in some of those cases is that the model was able to generate something that is not the exact reference word, but a generalization of it. For example, there was an out of vocabulary, which was a dog breed, which I can't remember what it was, but let's just say is a border collie or whatever, which is not in the vocabulary. But by seeing the image of a dog, the model just produced a word for dog. So the general word. So it's still not going to match the reference, but it's better than not having anything related there, right? Or having something completely out of context.
So how do you count these errors then, or generalizations?
We haven't done sort of a proper. This was sort of a manual inspection of the cases to see where the difference. We just looked at differences between multimodal and text only models. We did have some statistics, but this was a very small scale manual analysis. So it's hard to quantify that because you won't get it by any reference-based metric because it won't match the references either. And the cases of typos are quite interesting. I might be able to find it if there's another question, but where the system can actually really recover from that and generate the correct words. Any other questions?
If I may.
Yeah.
So I'm pretty much amazed by MMT, and I am sorry if I maybe missed that, but I wanted to know, what is your view? How is it going to be productized? What's the path to productized? Will it be something potentially that Google, Microsoft, Amazon, and all the other big IT adopts? Will it be open sourced? Is it currently available with commercial providers so that people can take advantage of it? So how does MMT make its way into the industry?
Yeah, so I think it's, I mean, it's still probably a bit early days, but I can tell you a little bit about possible use cases. I know that eBay was working on multimodal models because they have, with the picture of products, so they have to translate product descriptions into a number of languages. They want to machine translate that. And they were actually working on that. They have a paper on that now. I don't know whether they are productizing it or not. But for internal purposes, they might be using it. If there's anyone from eBay there, can let us know. In terms of use cases, social media platforms and mainly Facebook that has their own, say, translation model. I know there's interest there, and that's a clear use case. People post pictures and they tend to write a little bit of text, and for either to translate that, or they were actually also looking into generating descriptions for the pictures automatically for blind people. So that is exactly the use case that we had, that I presented, which is there is a model, not a human, but a model that generates description for the image, and then you also translate it into the language of the network of that particular user, so that they also get to see the description or to hear the description if they can't see the image. And so there are use cases out there in terms of whether this is viable in terms of speed and so on. I think this is another concern, because you do have this extra step of processing the image to extract the visual information, although the networks are pretty optimized at this stage, but there will be speed concerns if this is a real-time application. And the other one, the other use case that I would like to see happening, and been trying to collaborate with media or audiovisual companies, is really that of translating descriptions for blind people. So these are already produced by humans. They are already translated in a very large number of languages. And for some companies, at least that's how they do it. They produce a first version in, say, generally English, just like they do with subtitles, and then they translate it into various languages. And that is, you essentially need the video to generate that, and it can only help if you're translating. So if you're generating from scratch a description from the video, that is a very hard case. But if you're actually just translating an English description or whatever language description, the videos ought to help in that case. So I think these are clear use cases to me, but far from as far as I know, from commercial products at the moment, for reasons that I guess are I mean, it is early days, but also maybe people are still not even using machine translation for that in the last case, and so to move to a yet different type of machine translation may take a long time.
So maybe I can add something and combine it with a question. Now you have talked, I would say, rather about real life pictures. Has this been also applied to, say, artificial generated images, like a chart of stock and a description of or a recommendation of buy or sell or something like that? Because I could imagine translating these correctly would be a huge benefit if you can, say, consider the content of the images.
Yeah, that's an interesting use case. But I think it would require significant work into training different image networks to give you like better visual information on what that could be, because current visual networks are really just trained to either classify or detect things in the image that are very common objects. So if you had a plot or something that you want to describe, this would be a very different type of network, which I think, yeah, would be quite interesting, but I'm not aware of any work there.
Huh.
Another business idea.
Yeah, I mean, we are an applied conference, so this is also the idea. I think the comment of Konstantin, that's good for people who want to practice ahead of the curve.
Exactly.
One opportunity. So I think we are at the end of this session. As I said, there will be now, maybe I share again my screen briefly. We are at the end of this session. As I said, there will be now, maybe I share again my screen briefly. So we are at the end of this first keynote. First of all, Lucia, thank you very, very much that you took your time to give this interesting presentation. It was really a pleasure to have you here in inverted commas. And you will be around in the next session in the parallel tracks, which will start at 10 to 11. There will be several talks, and one will be another keynote session where we can discuss a little bit more in detail with those people who are interested to join. This will take approximately 1 hour. Afterwards is a lunch break, and then we meet again after lunch here in this large audience. So in the program that we sent you with the links, there are different links to the corresponding sessions, and we will have session chairs which are organizing these parallel. Thank you very much. And Lucia, enjoy the rest of the day. We will see each other in the session. And for the others, enjoy the break and see you later.
Thank you.